Ladies and gentlemen, I appreciate the opportunity to be here to do a presentation. My name is Zhou Tong. I come from Beijing University of Post and Telecommunications. The title of my paper is Dynamic Communication and Computation Resource Allocation Algorithm for End-to-End Slicing in Mobile Networks. I would like to share with you some of my research. My presentation includes 4 parts. First, let me introduce the background of my research. In the 5G era, Internet service objects and application scenarios have become diversified. With the increase in the number of user terminals, the growth of traffic scale, and the diversification of user demand, the current core network is becoming increasingly difficult to handle more and more diverse service requirements. As one of the core technology of 5G, network slicing can realize the transition from one-size-fits-all to one-size-per-service, which provides a new solution for the existing network. As is shown in Figure 1, during the past few years, there has been a growing consensus that 5G network slicing will support 3 generic services, which are classified as enhanced mobile broadband, massive machine-type communications, and ultra-reliable and low-latency communications. A network slice is an end-to-end virtual network in a mobile network, where a slice is constituted by a set of virtual network functions and links. The core network needs to be sliced, as are the bearer network and the RAN, and even the network controller and the terminal need to be sliced. In this study, we consider an end-to-end mobile network slicing system. The end-to-end network slicing architecture is shown in Figure 2. A complete end-to-end network slicing includes the core network slicing and the access network slicing. At present, most of the network slicing business requirements are dynamic. Therefore, the resource allocation process in network slicing will be affected by the randomness and time-varying nature of the actual environment. However, most of the work still stays in the fixed environment to optimize the instantaneous network performance index. In recent years, most of the work on slicing resource allocation only considers CN slicing or RAN slicing, and few studies consider the resource allocation of the entire end-to-end network slicing, and the process of network slicing deployment involves the joint allocation of multiple resources. So it is necessary to consider the dynamic allocation of communication and computation resource of end-to-end network slicing. Now let me move on to Part 2, Related Bases. This paper proposes an end-to-end network slicing dynamic resource allocation scenario as shown in Figure 3. Based on the mobile network end-to-end network slicing scenario with dynamic service requests, for dynamic network slicing services with a certain life cycle, considering the dynamic joint allocation of communication and computation resource in the end-to-end network slicing. This paper studies the use of online resource management technology to maximize the overall network utility on a long-term scale. In this model, graph theory is used to describe the underlying physical network and virtual network in the core network. The underlying physical network can be expressed as an undirected weighted graph. In the actual system, the specific resource requirements are usually related to the amount of data that VNF needs to process. Combine logical functions and generate a virtual network topology according to VNR. The VNR can be expressed as an undirected weighted graph. The process of mapping VNF to the underlying network is priced as M. In the computation resource pool on the access network side, each BBU provides the computation resource for RU to process baseband data. The BBUs in the computation resource pool can share their own resources, and all computation resources are centralized to form a virtual computation resource pool through virtualization operation. In the access network, a time-varying random channel model is considered. This model assumes that there are multiple RUs in a specific area. The total bandwidth is divided into multiple physical resource blocks. This PRBs is shared by all RUs. We construct the corresponding queue for data packets of each network slice service. On the right side, Qt is the queue length of the slice I of the user U at time slot t. The dynamic update process of Qt can be expressed as Qt equation 1. On the Cn side, Qt represents the queue length of VNF mapped to node n at the beginning of the time slot t. The dynamic update process of it can be expressed as equation 2. And delta t represents the computation resource allocation strategy in time slot t. Omega t represents the PRB allocation strategy in time slot t. Beta represents the mapping relationship between VNFs and physical nodes. The optimization goal of this model is to maximize the overall average network utility on a long-term scale of end-to-end network slicing, maximize the average network revenue, and minimize the average deployment cost when ensuring system transmission rate. The revenue comes from the service rate, and the expenditure comes from the VNF deployment cost, which can be expressed as equation 3, equation 4, and equation 5. Let's move on to the next part, proposed algorithm. In this paper, a two-stage Dqln algorithm is used to jointly allocate dynamic communication and computation resource in end-to-end network slice. The optimization problem to be solved can be modeled as a constrained macro decision process problem, which can be described by a for tuple. Where C is a finite set of states of the system, and A is a set of actions that can be taken. P is the probability of state C transition to C0 after performing action A in state in current time slot T. R is the reward function of state transfer to C0 after system executes actions A in state C, representing the instant cost or reward, which represents the learning goal. Dqln algorithm takes state C as input and outputs the corresponding action after neural network analysis. To fit complex environmental characteristics, it is necessary to repeatedly learn and train the weight function to improve the performance of network prediction. The training process of Dqln algorithm is shown in Figure 4. After the mini network of Dqln algorithm undergoes the training process, the optimal allocation scheme of network slice resources can be obtained by using the trained main network. The one-stage algorithm is a Dqln-based CN-side communication and computation resource joint allocation algorithm. The core network side optimization goal is to find the optimal VNF migration decision and VNF resource allocation strategy to minimize deployment costs. The dynamic allocation of CPU resource on servers in the physical network, the dynamic allocation of link bandwidth resource between servers, and migration strategy of VNF are described as a CMDP problem. So the input of CN-side algorithm is PRB allocation strategy and CPU resource allocation method that satisfy the constraints, and the output is VNF migration strategy and VNF resource allocation strategy. The two-stage algorithm is a Dqln-based runtime communication and computation resource joint allocation algorithm. The objective of access network side optimization is to find the optimal allocation scheme of PRB and computation resource under the premise of satisfying the constraints of the minimum service rate of each network slice and the constraints of network bandwidth resource, so as to maximize the network revenue. In the access network, the state of the system in time slot t is defined as CT, and the action in time slot t is defined as AT. The process of mapping state space to action space is defined as pi, which is a stability strategy. So the input of runtime algorithm is VNF migration strategy and VNF resource allocation strategy obtained by one-stage algorithm, and the output is PRB allocation strategy and CPU resource allocation method. The resource allocation process ends. Let's move on to the next point, simulation and resource analysis. In the simulation, this paper assumes that the network scenario is a fully connected network. The arrival process of sliced data packets is independent and identically distributed Poisson distribution, and the node failure rate and the link failure rate of the underlying network are uniformly distributed. The remaining simulation parameters are shown in Table 1. Figure 5 shows that as the time series progresses, network utility tends to stabilize. Compared with the PFSS algorithms and heuristic algorithm, the algorithm proposed in this paper can obtain the maximum network utility. Figure 6 shows the change in the average total slice rate of the three comparison algorithms as the number of users increases when the unit price of the service rate is 7. The average total slice rate corresponding to the three algorithms all increase with the increase of the number of users, and the algorithm proposed in this paper can guarantee the best system service rate. Figure 7 illustrates the change of the average size VNF deployment cost with the increase in the number of users in the three algorithms when the unit price of the service rate is 7. The simulation results show that the VNF deployment costs corresponding to the three algorithms all increase with the increase in the number of users. As can be seen from the figure, the algorithm proposed in this paper can achieve the lowest total system cost. Figure 8 shows, compared with the PFSS algorithm and heuristic algorithm, the algorithm proposed in this paper can obtain the largest average network utility. Now we are going to take a look at the last part, conclusions and outlook. This paper proposed a joint allocation method of dynamic communication and computation resource in an end-to-end network slicing scenario, aiming at the dynamic changes of network slicing data queues, radio channel status, and the physical network topology, constructs the end-to-end slicing dynamic resource allocation model. This paper proposed a two-stage communication and computation resource joint allocation algorithm based on Dqln. The simulation results shows that the scheme proposed in this paper can achieve the purpose of optimizing the overall utility of the network. increasing the long-term average revenue and reducing the average cost of the system. In the future study, we can consider more time varying conditions in a dynamic environment, such as a channel environment. We can also consider more comprehensive types of communication and computation resources, such as memory resources, network resources, and hard disk resources. What's more, the consideration of factors affecting the allocation of network slicing resources should be further improved, such as the mobility of the slicing and the server temperature. That's all my presentation. Thank you for listening.